yeah, there's going to be an online quiz again, or a quiz that you download and do online. So I'll post that up, and then let's say it'll be due Thursday, Friday, Sunday. Homework's due Sunday. Is that going to be a conflict? Make it due Sunday? All right. um, in 6.2, we found power series around what we call ordinary points, and those are points that are, ordinary. Uh, I'll say regular, but regular is also a keyword here. Except the button's still not clear. It's the same. Actually, that's a little bit better, but I should just get used to the buttons here. All right. Regular, ordinary, singular. Okay, so in 6.2, we dealt with what we call ordinary points, in that they don't have any issues with the denominators being 0, with stuff being undefined or anything like that. Yeah. About what? Oh. I think the term analytic is just our way of saying it's a nice function, and it's analytic in places where the denominator is not equal to 0 and things like that. Yeah. Yeah, that's all. That's all we're going to be testing for. The whole idea behind analytic is that a lot of times the functions that we're dealing with are analytic in most places, except for when things are denominators equal to 0. And that's the word analytic and radius of convergence and things like that. All those words really stem from studying functions and complex variables, complex analysis. And so the whole idea of radius, we think of radius as something that measures the length from the middle of the circle to the outer part of the circle, and that does come from complex analysis, because in the complex analysis, your variables are on a plane; they're not just on a number line. And so when we talk about all the possible points that you can put in, they come as a region, a circular region in your domain. Anyways, um, analytic just means it's continuous, it's differentiable, and it's nice. And usually, mathematicians go out of their way to find functions that are not analytic in special cases. So, anyways, in 6.2, we studied uh, finding power series solutions around an ordinary point, which was a point that had no issues. So now we're going to define a singular point. A singular point is not an ordinary point. So there's some issue with it, and there's different types of issues that could happen. And one of the issues that could happen is that this could be a 0 in the denominator, where it goes undefined. So that now defines a singular point. Now we're going to further categorize the idea of singular points by dealing with polynomials. And then we're going to say that if we take, we find these singular points by making the coefficient of the double prime equal to 1, and then dividing things out. And so really what you're looking at are places where a2 of x is equal to 0. And if it's equal to 0 at x naught, then that makes it a singular point. So we would have singular points based on this um, standard form of differential equation. And if our singular point in P is a singular point that's a linear singular point, and the singular point in Q is a quadratic singular point, then that's defined to be what's called a regular singular point. So in other words, if we had, let's just do a quick example here. Try to make sense out of this. If we had an x minus 2 squared y double prime plus x minus 2 y prime, and then we'll just say minus y or something like that, is equal to 0, then we get this into our standard form by dividing out that coefficient. Get y double prime is equal, no, not equal to, plus, now this is x minus 2 over x minus 2 squared, and a couple of x minus 2's will cancel out. And then the last term where it's just a regular function, it's just a 1 over x minus 2 quantity squared. So now we can identify our P, capital P, and our capital Q function. And then we notice now that it is a singular point because it's not analytic at x equals 2. Because if you put 2 in there, you get a 0 in the denominator, and that's not a good thing. So now that we know it's a singular point, let's check if it's a regular singular point or if it's an irregular singular point. So we do that by multiplying our P function by x minus 2, x minus our singular point, and our P function is equal to 1 over x plus x minus 2. And we notice now that this new little p of x function is analytic at 2 because it's just 1, it's a constant. So now that it's analytic, it means we're halfway through proving that this is a regular singular point. And we'll do the same thing and define a new function called little q, which is x minus 2 squared times big Q, and that's x minus 2 squared times -1 over x minus 2 squared, which again is a constant, and therefore analytic. So we can conclude that because of these two criteria that have been met, then we can say that it's x equals 2 is a regular singular point. For the differential equation. Okay? So we're kind of forcing ourselves to try to create a power series around a point like this. Now, the original differential equation, without having divided by, without putting it in standard form and stuff like that, the original differential equation didn't have any issues about being analytic. So we should be able to create a power series around 2 for this differential equation. But because of this idea that it's a regular singular point, we have to be a little bit more careful about how we come up with our power series. Okay, so we're going to create a power series around the singular point, but now because it's not an ordinary point, we have to be a little bit more careful, and we'll uncover some theorems. Okay, any questions? Yeah. Analytic means it's continuous and differentiable and nice and smooth. And so let's just say no zeros in a denominator at that particular point. Yeah. Again, well, you can call it piecewise. I mean, it could be analytic at some points, except for where it might not be smooth, and then it wouldn't be analytic at that point. Yeah. Differentiable, I think it's the nicer way to approach it. And again, the language of saying analytic comes from complex analysis, which you know, these differential equations are related to complex analysis because some of the stuff that we've done already dealt with complex variables, complex numbers. So it's kind of natural to be able to extend that, and they're extending all our definitions to some of those terms that we use in complex analysis. All right, let's take a look at our big theorem for this section, Frobenius. So this is kind of a strange theorem, but it's because it leaves a lot of things open when you're beginning a problem, and some of these things you'll find out as you do the problem, like there exists some R. What's R? And you have to figure that out along the way. So it says here, suppose that we have x naught as a regular singular point of a differential equation, then there exists one solution of this form, where this form looks like a power series, but the power series kind of starts at a different value of the power x. This is not, the constant, the linear, the quadratic terms. They introduce this R business, where R is a constant to be determined as we do these problems. And it says the series will converge for some sort of radius of convergence within the interval around x naught. And again, for simplicity's sake, we're going to be using 0, x naught is equal to 0, because that's just the easiest thing to do. If you start moving your x naught to a different place, the calculations will be, 3 times as hard, but the result could just be a function that's been shifted. So if we ever have an issue with having a different x naught, we usually try to shift it at 0, shift it at the origin. So we're going to try to determine what r is in the problem. And the way we're going to do that is we're going to come up with this indicial equation. Looks like initial. It's indicial, indical. Some equation that we're going to need to come up with. And again, we're going to make this nice and easy for us. We're going to assume that x naught is equal to 0. So we won't worry about any of those shifts. So when x naught is equal to 0 is our regular singular point, we're going to find our indicial equation by finding the power series expansion for little p and little q. And we defined little p and little q in the previous slide. But after we figure out what little p and little q are, the indicial equation will be determined by those constant terms of the series expansion for little p and little q. So we're going to figure out what a and b are equal to, and then we're going to come up with a quadratic equation in R that we're going to solve. And that's going to give us a value for R. Once we find the value for R, then we're going to put it into this form according to Frobenius. And then we're going to try hard as hell to solve for this series. Okay? Now, before actually doing an example, let's go through the possible cases, because when we have a quadratic, we got those 3 cases. We either got, repeated roots, we got 2 distinct real roots, or we got 2 complex conjugates for our R, for the solution for R. So let's figure out what to do in each of those cases. So once you figure out your indicial equation, you solve for it, and then when you solve for it, you're going to come up with 3 scenarios. Now, suppose you have 2 distinct. Oh, they only cover, we have those 3 cases, but the 3 cases aren't exactly the 3 cases that we normally think about for quadratic equations. Let's take a look at the cases that they have here. Case 1, when R1 and R2, the solutions are distinct and the difference is not an integer. So your solutions could be 1/2 and 1/4 or something like that. And then if you find the difference between them, the difference is not an integer. Then, this is usually the easiest case, I think. There exist 2 linearly independent solutions of the form C sub n is equal to x to the n plus R1, and then B sub n, x to the n plus R2. The initial equation is this weird equation where you have R times R minus 1 plus A times R, and A is the constant term of your little p of x. And then B sub 0 is that constant term for your little q. Yeah. maybe, maybe not, because remember our example that if it's going to be a regular singular point when you multiply it, this is our, like for example, this is our px in our example, and little px becomes 1, so it has to be analytic, right? And there, it might be possible that the constant term is actually 0 because every term has an x. It might be possible that that might happen, but it's not always the case, because the idea that this was a singular point means that when you multiply it by x minus x naught, then it's going to be a regular analytic function, and there's usually going to be a constant term. That's a good observation. All right, so back to the 3 cases. The first case, usually the easiest ones to solve for and the easiest ones to express, and maybe I should find a problem that has that, because I think the problem that I have is a little bit more complicated. The second case is that you have distinct solutions again, but now you take the difference, and the difference is an integer. So for example, solutions of 1/2 and 3/2, if you subtract them, you get a difference of 1. That's an integer. So if that's the case, then your differential equation will have solutions that are of this form, that will have a power series, and then the second one would be a power series times ln x. So that's also pretty easy to display, because you're essentially just looking for 1 power series, and then that's good to go. I guess the third case is that if they're equal, then there exists 2 linearly independent solutions, and the 2 solutions are get a little bit more complicated, get kind of twice as complicated. It takes a complication for the first one and the second one, puts it together, so now it's like 3 times as complicated. That's not good math. No, yeah. Ooh, are these the same? Maybe I should look at the book real quick. Anybody have the book? The 3 cases that they're presenting for Benioff's theorem, indicial equation. I think it's right. Yeah. So this thing has an extra c in it. Maybe is that the only difference? Oh, so this thing has an extra c. Yeah, I guess what we're doing here is that we're assuming, just to make things easy for us, that x naught is equal to 0. So if we assume that x naught is equal to 0, then that would make things a little bit easier. So yeah, if you take a look at these two the differences between these two, there's a really subtle difference. This one has an extra constant that might be equal to 0, and then you have y1 multiplied by ln x plus another one this one's raised to a different power. This one, r1 and r2 are equal, so it's raised to the same power. Oh, that's another difference. Brian, can you take a look? Oh, so so this is that's another difference. Okay, yeah. So there's another difference here when n is equal to 1 versus n is equal to 0. Oof. So I guess we're not looking at the differences when the differences are. We're not looking at the case where the the solution could be complex conjugates. Is maybe it can never be complex conjugates. Hmm. All right. So my example is a third case, and I don't know if I want to do that. Let's see if we can go to your homework set. I don't have my stuff prepared here. Let's do a homework problem. Wow, 9 problems. Damn. Oh, half of them are like figuring out if it's regular, singular. That's easy. Identify the function. Find the initial equation. So you don't really have to solve for any of these, except for this one. All right, let's try this one. No. All right, let's go through the process of trying to figure out how to solve for this differential equation by showing, first of all, showing that it is a regular singular point and then figuring out what the initial equation is. And then finally trying to attempt to solve for this. All right, so we have our a2 of x. We want to divide that. So let's write this in the form that we want. We got y double prime by itself. You got 1, oops, this is a plus, 1 over 6x times y prime plus 1 over 3x times y is equal to 0. So we're assuming that x naught is equal to 0 to make things easy for us. And so our capital P of x is 1 over 6x, and our capital Q of x yeah, so our term x minus x naught in Frobenius's theorem will just be x. Yes, yes, yeah. Yeah, if you had an x minus 2 or x minus 1 or x plus 7 or something like that, then there's a shift going on. Yeah, you would still 1, right? Yeah. Okay. And if you ever do come up with these problems where there's your x naught is not 0, you can always try to shift it to the origin or shift it so that your x naught does become 0. Because, like I said, dealing with these x minus x naught business where x naught is not equal to 0 gets a little gets that much more complicated when you're doing these power series. All right, now that we've identified P and Q, let's identify little p and little q. So little p of x is x times capital P of x. So that's 1/6. And little q of x is going to be x squared times 1 over 3x. And so this is going to equal to 1/3 times x. Okay. Oh, I guess we also, from here, we want to identify our A naught and B naught to help us find our indicial equations. So if you imagine this is a power series, you have a constant term plus 0 times x plus 0 times x. Not that this matters, because the only thing you're really focused on is a constant term. And so your A naught is going to be 1/6. Okay. Similarly, over here, um, you have to write it as if it was a power series, and so there's a constant term, and then the 1/3 happens to be a linear term, and then everything else is 0. But we do want to keep an eye on our constant term, and in this case, B naught is equal to 0. So now we can create our indicial equation. What was it? R minus 1 plus or minus 1/6 R plus or minus 0. I don't know. I'm just making it up now. Yeah. A thing? Yeah, yeah. Well, the idea is to identify the constant term. And if you have a polynomial, like in this case, we have 1/6 and we have 1/3 x. Those are polynomials, and that's easy to figure out what the constant term is. But for some reason, if you had an e to the negative x there, which could happen, probably not in our class, but it could happen, then you would expand it as a series and figure out what the constant term is. What the constant term. And that helps find your A naught and B naught for your indicial equation. Now, before you write this down, did you guys check what the indicial equation is? Plus, plus, so they're both pluses in R minus R times R minus 1. Yes. So if we had this as a singular point and you see that there's another singular point for the same differential equation, then yeah. All right, we have a quadratic that we need to solve for. Let's see, we got R squared minus R plus 1/6 R, and that's it, 0. Suppose we can factor out an R, and then we can combine -1 plus 6 is -5/6. So R is equal to 0 and R is equal to 5/6. And the difference between them is not equal to 1. Let's call this R1 and R2. So they're distinct real number solutions, and R1 minus R2 equals -5/6. Not an integer. So we're in the first case. Um, we're in case one, the three out of the three cases. So R1, R2 are distinct. The difference is not an integer, and then so we have to find two linearly independent series of this form. Okay. Are we good so far? 0 is a nice number because that'll make one of our series look like just a regular power series. This additional equation? That's how, yes, this is how you're finding your roots. And then this is how you're finding your R's, which kind of helps dictate how your solutions are going to look like. All right, let's figure out the first one. When R is equal to 0, according to this, our three cases, one of our solutions is going to be of the form C sub n x to the n plus R1. And if, like I said, if R is equal to 0, then this is just like a regular power series. So let's assume that our solution, y1, is going to be of the form series n goes from 0 to infinity of C sub n x to the n plus R1, which in this case is equal to 0. And then this is just like a regular power series solution. So we've done this, I think. You've done it at least one time. Well, if you participated in the thing. And so let's find the solution. This is where we go through the steps of finding the derivative and second derivative and putting it into the differential equation. We can put it into the original differential equation, by the way. We don't need to always come back to this standard form differential equation. So that's what we'll do. So y1 prime is going to equal to the series starting from 1 to infinity this time, and c sub n x to the n minus 1. And then the second derivative is going to be starting from 2 and n minus 1, c sub n x to the n minus 2. And let's drop that into our differential equation, which is 3xy double prime. What's it again? Plus 1/2 y prime plus y. And so we got 3x series. The second derivative starts at 2 to infinity, and n minus 1, c sub n, x to n minus 2. And then we got a 1/2. The first derivative starts from 1 and c sub n x to the n minus 1, and then plus y, which is a series that starts with 0. And that's cn x to the n. Now let's multiply this through. The starting index is the same. We got 3. And we got some constants, n minus 1, c sub n. Now we had that extra x. So we're going to get x to the n minus 1 from n minus 2 because we threw in an extra x. Let's throw the 1/2 inside of the series. And this starts from 1 to infinity, and then the other one doesn't change. Now let's shift series. So let's shift it to make it look like x to the n. So we add 1 to this first series, we subtract 1 to the index. And I don't know if you guys want to change the indices from n to k. Let's change it to k. Okay. This time we add 1 to the ends inside, so we subtract 1 to the index. So instead of starting with n is equal to 2, we're going to start with k is equal to 1. And then we're going to add 1 to everything else in here, k. So now we have x to the k power. This one, we need to do the same thing, add 1 again, inside, subtract 1, so our k starts with 0 now. 1/2, add 1, so that's k plus 1, c sub k plus 1. So the k, matching powers, and then the other one doesn't change. Except change the variable to k since they're all the same. They don't have to be all the same, but it's nicer that way. So we got k is equal to 1 as an index, so we want to extract k is equal to 0 for these two series, so that we all have matching k starting point and k is equal to 1. So k equals 1 to infinity. I'm just rewriting the first series. Now for the second series, I'm going to extract the k is equal to 0, so I can have my series starting at k is equal to 1. So when k is equal to 0, I get 1/2 0 plus 1, k to the 0 plus 1, and x to the 0 power, which is just going to leave it as a constant or make it into a constant. And now, meanwhile, I have my series. Since I took the k is equal to 0 term out, I'm going to start my series at k is equal to 1, and everything else stays the same. And then I'll extract the same information over here when k is equal to 0. And then the rest of this when k is equal to 1. So I have my constant terms because x to the 0 power is just 1. So I basically have a constant term. And then that would find a relationship between C1 and C0. And I'm going to move that in front. So 1/2 C1 plus C sub 0. So those two terms are gone, taken care of here. X to the 0 power is just 1, so that's constant. And then everything else can go into one series because the series now starts from 1 to infinity. And in each of these series, there's a couple of things to think about factoring. One, we can factor out an x to the k since we made it so that they have the same x to the k power. And then the other thing to do is to collect all the terms with a c together with the same c subscript. So I'm going to collect the c sub k together. That's 3 k plus 1 times k plus 1/2 k plus 1. So that has a k plus 1, c sub k plus 1 multiplied next to it. And then the other term that we have left that's x to the k is just c sub k. Maybe I should have done this in 2 steps, but I just collected the terms that are underlined, double underlined here, and then I factored out a c sub k plus 1. And then in the same step, I took out this term that has a c sub k, only c sub k. Because in my relationship between c sub k plus 1, I want to see this happen. Okay. I also factored out next to the k. Good. So this is homogeneous. So we're going to set everything equal to 0. We're going to set 1 half c sub 1 plus c sub 0 equal to 0. That's going to give c sub 1 is equal to minus 2 c sub 0. And that's our first relationship. And notice that usually when you deal with second order differential equations, we see two patterns emerge, usually relating the odd subscripts and the even subscripts all together. And then we come up with two linearly independent solutions. We see that we're not getting that here, right? Because this is not an ordinary point. This is a singular point, regular singular point. So we're only going to get one linearly independent solution. We're only going to get one solution from this work, which means Frobenius tells us that the other solution is going to come in the form with an R in it. And we're going to get there. All right, if I set this equal to 0, our relationship is going to be c sub k plus 1, because that's what I want. I want c sub k plus 1 is going to be negative c sub k, and then divide by this whole constant. Is there anything we can work out here? Maybe factor something out? We can factor out a k plus 1. Yeah. This might work nicely. Yeah, so it's kind of tricky if you're trying to find a pattern. You might, want to maybe not simplify this, and then versus simplifying it, that might look like I don't know if I can catch a pattern emerging with a k plus 1 and then 3k plus 1 half. That looks like a weird thing. Versus seeing something like 3k plus 1k plus 1 half k plus 1. The pattern might come out nicer if I keep it looking like this. But we'll see. We'll take a look. And this works for k starting with 1. So that's what we'll do. We'll find the pattern. So when k is equal to 1, we got c sub k plus 1, which is 2. It's going to equal to minus c sub 1 divided by, now let's put a 1 in here. This is going to be a 2 times 3 7/2. Is that right? So that's minus 1/7 c sub 1. But c sub 1 is equal to negative 2 c sub 0. So positive 2/7 c sub 0. Right? I hope. Okay. Let's do one more. When k is equal to 2, we have c sub 2 plus 1, it's 3, is equal to minus c sub 2 divided by, okay, k is equal to 2, so this is going to be 3 times k is equal to 2 6 plus 1/2, 6.5, 12, 13 halves. So this is where we might lose this pattern catching, trying to find a pattern. So this is 2 over 39 negative, and then c sub 2 is equal to 2 over 7 c sub 0, and then that gives us c sub 3 is equal to negative 4 over whatever, what's 39 times 3, 6, 1, 8. Is that right? 273? Let me check the answer. Uh-oh. Oh, that puts you, oh, that should make a difference. $273. So how'd you get 27? Wait, 273? I don't know. 247. I don't know. Looks like we got 2 7s here. This looks like it might be it. It means I have 4 over 273. Oh, it is here. Okay. Ooh. It's negative, right? Negative 4 over 273. And that's the c sub 3, which is multiply x3. All right. So, okay, good. But this is the first answer, right? This is the y sub 1. So we need to find y sub 2, and y sub 2, I suppose we should go to the next page. And we need to figure out this differential equation when r is equal to 5, 6. So let's continue on. You can read my writing. Continued. Good. So now we're going to say r is equal to 5, 6. And according to Frobenius, our second solution should look like this. y2 is going to equal to, how does it look like? B sub n, x to the n plus r, and then b sub 0 is not equal to 0. So let's see what we can do with that. So this is going to be the series n goes from 0 to infinity of b sub n x to the n plus 5/6. Well, if we approach it the same way we did last time, which is to take the derivatives and then put it into the equation, then that's what's supposed to happen, right? If this is in fact supposed to be um, a solution, then its derivatives should work. So the derivatives are going to look a little funkier than before because of that extra r that comes up. And so we have, instead of just an n, c sub n, x to the n minus 1, it's going to be n plus 5/6 b sub n x to the n. We subtract, right? Subtract 5/6 minus 1, negative 1/6, right? And then our second derivative, oops, this should be a 1. Our second derivative, n goes from 2. Whoa, wait a minute. I have to think if the index needs to shift. Let's write out a few of these terms. N is equal to 0. I have b sub 0, x to the 5/6 plus b sub 1, x to the, add 1, 5, 6, 11/6. So if this is y sub 2, then y sub 2 prime is going to be 5/6 b sub 0 x to the negative 1/6 plus 11/6 b sub 1 x to the 5/6. Right. So we still do have a b naught term in the derivative, which means that when we take the derivative of this still starts from 0. Is that correct? Would you guys agree to that? This is so hard. What else can you say? Just say yes. So yeah, we're going to do it again, and we're probably still going to keep it at 0 here. All right, so we got n plus 5/6, n minus 1/6, b sub n x to the, I need to subtract 1, so it's going to be n minus, is it 5 or 7/6? 7/6. Okay. So why don't we take those and plug it in to our differential equation. What was it again? It was 3x. Well, let's use a different color pen here. Not that it helps anymore. It's just all confusing now. 3x, y double prime, and then there's a plus. 1/2 y prime plus y is equal to 0. So we got ourselves a 3x times the second derivative, n goes from 0 to infinity, n plus 5, 6, n minus 1, 6, b sub n, x to the n minus 7, 6, plus 1/2 n plus 5, 6, b sub n, x to the n minus 1, 6. Same index starting at 0 to infinity. And then our last one, b sub n, x to the n minus 5, n plus 5, 6. All right, multiply some stuff out. Same thing, right? Multiply stuff out, match the terms. So we got n going from 0 to infinity, n plus 5, 6, n minus 1, 6, b sub n, x to the, oh, there's a 3 in there. Let's throw a 3 in there. And then there's an x that we get to add. That's going to be n minus 1, 6 after we add an extra x. And then we have our second series. 1/2 goes in, n plus 5, 6, b to the n, x to the negative 1, 6. So they have the same power. That's good. The last one doesn't have the same power. Let's just change the last one. So basically, we want our k here. We let our k equal to, what is it again? Say it again. K is equal to, okay. So we're essentially adding or subtracting 1 to this. So k is equal to, if we bring it over to the other side, n plus 1, or n is equal to k minus 1. So the shift is still a plus 1 or a minus 1 because we're dealing with indices here. And I hope it works out like that. If it wasn't. So let's go with our series starting. So we subtract 1 and we add 1. So that if you guys could try to remember the whole subtracting and adding, and we're really subtracting or adding 1 or 2 or 3 or something like that, that's what we're going to do here. We're there. We're here. Here, there. Then k would equal, no, the starting point would be 1, right? If it's 5 over 6, then the shift is still going to be 1 up or 1 down, right? So we're not shifting these two series. We're only going to be, did it work? No. Oh, there it goes. Yeah, so this is the only thing that we're going to shift. Let's see what happens to the shift. And so we got k. We want to match this up, so we're going to imagine subtracting 1 from the inside of the series. So all the terms inside of the series will be 1 less. And then now your starting point will be 1 more. Oh, we switched to k. Let's switch to k. So then we need to take out the n is equal to 0 for the first two series. All right. Why don't I not write that out and just say that? Oh, I was going to write the same thing, right? I mean, I can copy and paste and all right. So now from here, maybe it's worth changing colors again. I want to take my n is equal to 0 out, or k is equal to 0. Did we switch to k? Are you guys okay with switching to k? Just say yes. All right, k is equal to 0. I have 3. Why is my stuff is moving? It shrunk. What? 5/6, negative 1/6, b sub 0, x to the negative 1/6. Plus, I took the 0th term out, so now I'm going to start with k is equal to 1, and then goes off to infinity, and then I'll just rewrite everything over with k's. Okay, so that's that first term right here. Now let's get to the second term. Again, k equals 0 gets taken out. So I get a 1/2, 0 plus 5/6, b to the 0, x to the 0 minus 1/6. And then now I have my series. That's exactly the same, except I'm starting with 1 because I took out the 0th term. And then the last thing I have here is my third series. K goes from 1 to infinity, b sub k minus 1, x to the k minus 1/6. And they all have x to the k minus 1/6, which is where I want to be. And then they all have the same index starting at k is equal to 1. And so let's take these ones that are underlined, and they both have an x to the 1/6 associated with them in the b naught. They both have b naughts? Yeah, yeah, so b naught's going to be equal to 0. So I have 3 times 5/6 times negative 1/6 b naught plus 1/2 5/6 b naught times x to the negative 1/6. And if this is going to be equal to 0, we're solving for b naughts or finding relationships with b. So looks like b naught's going to be equal to 0. Wait a minute. That's what? What should b naught be? 0. But this has to equal to 0, right? Oh, this is a different b naught. See, The tricky part here is that b naught's supposed to not equal to 0. Ah. Oh wait, is it actually equal to 0? Yeah, somebody said that. Yeah, the whole term's equal to 0, and so that leaves b naught can be anything. So b naught can be anything because these terms make it go to 0 anyways. So that's good. So b naught's not equal to 0 according to the theorem, or the three cases. B naught's not going to be equal to 0. So now let's collect. Should have done this in a different color. Let's collect these other terms in the series. So let's put. So this thing is 3 times 5, 6 minus 1, 6. So this whole thing is going to be equal to 0 regardless of what b naught is equal to. So b naught can be anything. All right, so let's put all these things together into one series, and then we'll take the coefficient out and set it equal to 0. So again, I'm going to look for the ones with the same b sub k. So I'm going to get a 3k plus 5, 6, k minus 1, 6. And then there's a bk here, but there's also a bk here. So I'm going to put that together, 1/2 k plus 5, 6 bk. And then there's a plus bk minus 1. And then they all have an x to the k minus 1/6. All right. So you just need to solve for this. bk is equal to minus bk minus 1 divided by this whole thing. And you can keep it like this so you can factor some stuff out. Looks like maybe we can factor out a k plus 5, 6. And then if we do that, we have a 3k minus 1/6 plus 1/2. What? Yeah. So we have k's here. When this starts when k is equal to 1, when k is equal to 1, this is b sub 0 and b sub 1, and you can set your pattern. In any case, let's try our answer based on our first solution. Is it right? Oh, there's a check mark. Okay, so that's the process. What I can do is I can finish this up and then write it up and then post it online some other time, and then you guys can try to follow along. And yeah, good luck with the homework. Homework isn't bad. Homework is all the stuff that's before this, except maybe for one. So I'll post a quiz online. It'll be due on Thursday or Sunday or something. Sunday.